Hello. In this video, we're going to be looking at summation notation. This is Appendix E in your textbook. And as we go through this video, I just encourage you to take detailed notes. Summation notation was covered in grade 11, but it's been a little while since you've looked at it, so I just want to make sure that you have good notes going forward on this topic. The motivation for this section is the following question. What is 1 plus 2 plus 3 plus all the way up to 99 plus 100? Well, if we look at the first couple terms, we could probably do it in our head. 1 plus 2 plus 3, that would give us 6. Maybe we could add another 4 and get 10, plus 5 would be 15. If you had a calculator handy, you might be able to start adding up the first couple terms. But you'd probably find it gets a little monotonous, a little tiresome to keep adding and adding and adding all the way up to 100. And it would be nice if there was a shortcut, a faster way of adding all the way to 100. Now, hopefully, through this section, we're going to be able to develop a way of doing this a lot quicker than just brute force adding 100 numbers. And if you want, you can pause the video and try adding up the numbers 1 to 100. But we're going to take a look at summation notation to try to help us do this a little bit better. So the first thing we're going to look at is the definition of summation notation. So let A1, A2, A3, all the way up to AN be numbers or functions. Then their sum is the following. A1 plus A2 plus A3 plus ... plus AN. We write it as equal to, and this is how this is pronounced, this is the sum from I equals 1 to N of AI. Now, and feel free to pause the video at any point if you need to copy something down. Now, again, this is read the sum, I equals 1 to N of AI. Well, maybe we should do an example to try to understand what that means. What if we were going to do the sum as I equals 1 to 4 of I? Well, the way to think about this question is we're going to start off at I equals 1. And we're going to finish up at I equals 4. And all along the way, this expression right here, this I, is going to be what we're adding. So when I is equal to 1, the first term, we just put 1 plus. And now we increase. So I is equal to 2. Well, when I is 2, the expression is just 2 plus. Then we do I equals 3. So we write a 3 plus I equals 4, 4. And we write equals 10. If we added it all up, one after another. Now how about this? I equals 1 to 7 of I squared. So let's try to break this down. We're starting at I equals 1, and we're going all the way up to 7. So that's what the 1 and the 7 mean. Now the I squared, it means that each time we do the sum, for each term in the sum, we're going to be squaring it. So we start off with I equals 1, and we get 1 squared, plus. Then I increases to 2, and we write 2 squared. And then we write 3 squared, and 4 squared, and 5 squared, and 6 squared, and 7 squared. And then we see the top number here is 7. So that's where we stop. We stop at 7, and so we have all the squared numbers from 1 up to 7. Now if we were to do a little arithmetic here, if we know our squares, this is 1, this is 4, 9, 16, 25, 36, and 49. So if you have a calculator handy, or if you were to do some long addition, eventually you would get the number 140. Okay, so we kind of have a bit of a grasp on how that might work. Let's try another example with a function. So here we have the sum, I equals 1 to 4 of sine I pi over 2. Well, let's try the same thing. We're always going to write out this expression, and each time I starts at 1, 2, 3, and then up to 4. Everything else in the expression remains the same, but we have to change the value for I. So first we write sine of 1 pi over 2 plus Then I increases. Sine of 2 pi over 2 plus sine of 3 pi over 2 plus sine of 4 pi over 2. And then we stop because I gets to 4. Okay, so can we simplify this? Can we turn this into a number? Well, sine of pi by 2 is going to be just 1. Sine of 2 pi by 2, or sine of just pi, is 0. Then we have minus 1, and then we have 0. So we actually get that this sum is just 0. Let's try another example. This one a little bit more interesting. So here we have the sum, I equals 1 to 5, of I plus 1 squared minus I squared. So again, we're going to follow the same idea. When I equals 1, we're going to have 1 plus 1, or just 2, squared, minus 1 squared. Right? When I is equal to 1, we get 1 plus 1, which is 2, so 2 squared. And then we get a 1 squared, and they're subtracting. This is all the first term in our sum. Then we put plus. I goes up to 2, so you get 2 plus 1, which is 3 squared, minus 2 squared. Okay, we go up another one, so 4 squared minus 3 squared, plus 5 squared minus 4 squared, plus 6 squared minus 5 squared. Now, the reason we're looking at this sum here is because this one actually has a really nice property. And we're going to talk about it a little bit more on the next page. But if you look here, we don't have to use a calculator to do all this. Now, you could work out all the squares and you could calculate it all. You would find that the answer would be 35, I believe. But there's actually a bit of a shortcut here. If you notice, there's a 2 here and a negative 2 squared. So what we can do is, we'll simply cancel those off. And if you look here, there's a 3 squared and a negative 3 squared. So again, we can cancel these off. What else is the same? There's a 4 squared and a minus 4 squared. We can cancel those. And there's also a 5 squared and a minus 5 squared. So all we're actually left with here is a minus 1 squared plus a 6 squared. And just for purposes of the next example, we're just going to leave this as a 6 squared minus 1. We're not going to bother squaring the 6. I know we could simplify this to 36 minus 1, which would be 35, but we're just going to leave it in this form, and it'll make more sense when we do the next example. Now we have here a little bit of a strange sum. We have the sum, I equals 1 to n. Okay, so that part's a little bit strange. And it's of I plus 1 squared minus I squared. So the first strange thing is we're going all the way up to n. And the other strange part too is that this is a very weird expression. Although it is the same expression we had from before, so I think we're decently equipped to handle it. The way it works is we start, as before, I equals 1. So 1 plus 1 squared is 2. So we have 2 squared minus 1 squared. Plus 3 squared minus 2 squared. Plus, well, we could write another term if we wanted. 4 squared minus 3 squared. And we're just going to keep doing this all the way up to n. N is an arbitrary number, so we can put plus dot dot dot. When we get to n, let's think about what that last term in our sum will look like. It'll be an n plus 1 squared minus n squared. So we can write that. N plus 1 squared minus n squared. Now again, we get out our colored pen and we see what cancels. Well, the 2 squareds cancel just like before. The 3 squareds will cancel. And if you think about it, this 4 squared, if we would have written out another term, the 4 squared would have canceled with something in there. The next term would have had a negative 4. That would have canceled, and so on and so forth. Eventually, everything's going to cancel, and even this final n squared will cancel with something in here. And so all we're going to be left with, just like the previous example, is a minus 1 squared plus n plus 1 squared, which we can rewrite in the nicer form, n plus 1 squared minus 1. Now this will prove very useful for us later on in the lesson, but for right now we can just appreciate that we had a very large sum and we were able to reduce it down to a much simpler expression here. If you think back to the other one we were summing up to 5, and our final answer was a 6 squared minus 1. We can see here that that's just a special case of this. 5 plus 1 is 6, so 6 squared minus 1. We have a special name for these types of sums. They're called a telescoping sum. The name comes from the idea of if you had one of those old telescopes, you might be kind of out at sea, right? It might kind of have one section here, and then it might have another section kind of here, and then it might have another section here, and you could kind of imagine collapsing the whole thing, so it would kind of collapse in on itself, and you'd just be left with a very small kind of telescope that would be kind of all bundled up together. It would extend out like a slinky, and then it would crunch down like a telescope. So that's where the idea of a telescoping sum comes from. Now, we can do a few others. Let's take a look at this example. I equals 1 to n of I plus 1 cubed minus I cubed. We're going to do the same method as before. I equals 1 means 1 plus 1 cubed, so 2 cubed minus 1 cubed plus 3 cubed minus 2 cubed plus 4 cubed minus 3 cubed plus ... And the last term will be n plus 1 cubed minus n cubed. Again, if you look here, there's a 2 cubed and a negative 2 cubed. We can cancel those. We can cancel the 3 cubed. We'll be able to cancel the 4 cubed with the next term, we just didn't write it. And we'll be able to cancel the n cubed with a term in here as well. So really, all we're left with is minus 1 cubed plus n plus 1 cubed, which we can rewrite as n plus 1 cubed minus 1. Now, again, you should see the pattern here, similar to the previous one. If we scroll up here, it was n plus 1 squared minus 1. This one is n plus 1 cubed minus 1. So for homework, I want you to do the same idea. I want you to do the sum I equals 1 to n of I plus 1 to the 4 minus I to the 4. And you should get n plus 1 to the 4 minus 1. It's the same idea, it's just going to be to the power of 4 instead of to the power of 3. Now one more item we're going to look at before we're done for the lesson is rules for summation. Now we're going to look at a few rules, and we're just going to focus on the first rule here. It says summation distributes over addition. Now this can be rewritten in math as the sum I equals 1 to n of ai plus bi is equal to the sum of ai plus the sum of bi. Now I like to remember it in kind of a funny way. If you remember, the limit of the sum is the sum of the limits, or the derivative of a sum is the sum of the derivatives. In this case, instead of doing a limit or a derivative, we're doing a sum. And so this result really says the sum of the sum is the sum of the sums. So the sum of the sum is the sum of the sums. I think it's kind of a clever way to think about it. But if you don't like it, you can just remember the formula we have here. So let's take a look at the proof. How would we prove something like this? Give some evidence. Well, we'd start with the left-hand side here. So we'd start with the sum I equals 1 to n of ai plus bi. And if we wrote this out, this would be a1 plus b1. And then when I equals 2, it would be a2 plus b2. And then when I equals 3, it would be a3 plus b3. And so on and so forth, until finally we got to an plus bn. Now what we would do is, we look here and we have an a1, we have an a2, we have an a3, all the way up to an. We're just simply going to rearrange the formula by writing all the a's first. So we'll have an a1, we'll have an a2, we'll have an a3, all the way up to an. And then of course we'll write the b's. So we have a b1, we have a b2, we have a b3, all the way up to bn. But if you look here, a1 plus a2 plus a3 plus all the way to, plus an and plus bn, this is actually the sum as I equals 1 to n of ai. So we could rewrite this here as the sum I equals 1 to n of ai. And here we have b1 plus b2 plus b3 all the way to bn. This is simply the sum I equals 1 to n of bi, which is exactly what we wanted to show. In the next lessons, we'll take a look at more rules of summation, but for now, make sure you're comfortable with the basic summations as well as the summations up to n that we showed above. Thanks for watching.